Explanation: the Hall effect is like watching a river electric current flow through a narrow channel while a strong wind magnetic field blows across it. The wind pushes the floating leaves charge carriers sideways, creating a small pileup on one side of the riverbank. That pileup is a difference in electric potential, the Hall voltage V sub H. Mathematically, consider a rectangular slab of material with thickness T, width W and length L. A current I flows along the X direction, and a uniform magnetic field B equals B hat Z points out of the slab. Each carrier of charge Q moving with drift velocity V sub D feels the Lorentz force F equals Q times V sub D cross B, because V sub D is along X and B along Z. The force points toward the Y direction, pushing carriers to one side. In steady state, the electric field E sub Y that builds up exactly balances this magnetic force. Q E sub Y equals Q V sub dB, which implies E sub Y equals V sub dB. The Hall voltage is the integral of this field across the width. V sub H equals E sub Y times W, which equals V sub D times B times W. Since current density J equals NQ V sub D, with N carrier concentration, we can write V sub D equals J divided by NQ, which also equals I divided by NQTW. Substituting gives the classic Hall voltage formula. V sub H equals I times B divided by NQT. This simple picture explains why the Hall voltage is proportional to current and magnetic field, and inversely proportional to the thickness and carrier density. The derivation also shows the sign of V sub H depends on the sign of the charge carriers, positive for holes, negative for electrons. This sign sensitivity makes the Hall effect a powerful tool for identifying the dominant carrier type in a material. Explanation: the Hall coefficient RH is defined as the ratio of the measured Hall electric field to the product of current density and magnetic field. RH equals E sub Y divided by J sub X times B. Using the relationships from the derivation, we substitute E sub Y equals VdB and J sub X equals NQVd. RH equals VdB divided by NQVdB, which simplifies to 1 divided by NQ. Thus, RH is simply the inverse of the product of carrier concentration N and charge Q for a material with a single carrier type. The magnitude of RH directly tells us how many carriers per unit volume are present. N equals 1 divided by the absolute value of RH times the absolute value of Q. In real semiconductors, both electrons, negative, and holes, positive, may contribute. Then the Hall coefficient becomes a weighted sum. RH equals open parenthesis P mu sub P squared minus N mu sub N squared close parenthesis divided by Q times open parenthesis P mu sub P plus N mu sub N close parenthesis squared, where P and N are hole and electron concentrations, and mu sub P, mu sub N are their mobilities. If one type dominates, the formula reduces to the simple 1 over NQ or negative 1 over PQ form. Carrier density determination. Step 1. Measure the Hall voltage VH for a known current I, magnetic field B, and sample thickness T. Step 2. Compute the Hall coefficient. RH equals VH times T divided by I times B. Step 3. If a single carrier type is assumed, find N equals 1 divided by the absolute value of RH times Q. Step 4. If both carriers exist, solve the two-equation system using the measured RH and the conductivity sigma equals Q open parenthesis and mu sub N plus P mu sub P close parenthesis to obtain N, P mu sub N mu sub P. The sign of RH tells you whether electrons, negative RH, or holes, positive RH, dominate, which is why Hall measurements are a standard method to identify the type of a semiconductor. The Hall effect shows up in many kinds of materials, but the details depend on how charge moves inside them. 1. Metals good conductors. In a metal, many free electrons wander like a crowd in a busy hallway. Because the number of carriers N is huge, approximately 10 to the 28 per cubic meter, the Hall coefficient R sub H equals 1 over NQ and is tiny. The resulting Hall voltage is often only a few microvolts, requiring careful instrumentation. The sign is negative because electrons are the carriers. Example, in copper, R sub H is approximately negative 5 times 10 to the minus 11 cubic meters per coulomb. So a 1 millimeter thick copper strip carrying 10 amperes in a 1 Tesla field would produce only about 5 microvolts. 2. Semiconductors. Doping creates far fewer carriers, 10 to the 21 to 10 to the 23 per cubic meter, so R sub H is orders of magnitude larger, giving easily measurable Hall voltages. By adding donors N-type or acceptors P-type, you can flip the sign of V sub H. This is used to confirm the doping type. Mobility mu is also larger in semiconductors, so the Hall effect becomes a window into both N and mu. Example, in N-type silicon with carrier concentration N equal to 5 times 10 to the 21 per cubic meter, and electron mobility mu sub N approximately 1,400 square centimeters per volt second. The Hall coefficient R sub H is about negative 1.25 times 10 to the minus 3 cubic meters per coulomb. 3. Ferromagnets. In addition to the ordinary Hall effect, abbreviated OHE, described above, ferromagnetic materials exhibit the anomalous Hall effect. Abbreviated HE here, the Hall voltage has an extra term proportional to the material's magnetization M. V sub H equals IB divided by NQT plus IR sub SM divided by T, where R sub S is the anomalous Hall coefficient. The anomalous Hall effect can be much larger than the ordinary Hall effect, and is used to read magnetic states in hard disk read heads and magnetic RAM. The mechanism involves spin-orbit coupling, which bends the trajectories of spin-polarized electrons. Example, in a thin film of permalloy nickel iron, the Hall voltage at low fields is dominated by the anomalous Hall effect, providing a direct electrical measure of the film's magnetization. In all cases, the core idea is the same. A magnetic field deflects moving charge, but the magnitude, sign, and extra contributions differ with the material's internal electronic structure. Example 1. Hall voltage in a silicon wafer. Given N-type silicon wafer, thickness T equals 0.5 millimeters, current I equals 5 milliamps, magnetic field B equals 0.2 Tesla, electron concentration N equals 1 times 10 to the 22 per cubic meter. Hall coefficient. R sub H equals negative 1 over NQ equals negative 1 divided by 1 times 10 to the 22 multiplied by 1.6 times 10 to the minus 19 equals negative 6.25 times 10 to the minus 4 cubic meters per coulomb. Hall voltage using V sub H equals R sub H IB divided by T. V sub H equals negative 6.25 times 10 to the minus 4 times 5 times 10 to the minus 3 times 0.2 divided by 5 times 10 to the minus 4 approximately equals negative 1.25 times 10 to the minus 3 volts, which is negative 1.25 millivolts. The negative sign indicates electrons dominate. Example 2. A determining carrier concentration in a metal. Measured Hall voltage V sub H equals 8 microvolts for a copper strip, current I equals 2 amps, magnetic field B equals 0.5 Tesla, thickness T equals 0.2 millimeters. Compute Hall coefficient. R sub H equals V sub H times T divided by IB equals 8 times 10 to the minus 6 times 2 times 10 to the minus 4 divided by 2 times 0.5 equals 1.6 times 10 to the minus 9 cubic meters per coulomb. Carrier density assuming electrons. N equals 1 over absolute R sub H times Q equals 1 divided by 1.6 times 10 to the minus 9 times 1.6 times 10 to the minus 19 approximately equals 3.9 times 10 to the 27 per cubic meter, which is typical for copper around 8.5 times 10 to the 28 per cubic meter. The difference shows measurement errors or mixed contributions, common in practice. Example 3. Anomalous Hall effect in a ferromagnetic thin film. Given permalloy film, thickness T equals 100 nanometers, current I equals 10 milliamps, external field B equals 0.05 Tesla, ordinary Hall coefficient R sub O equals negative 2 times 10 to the minus 10 cubic meters per coulomb, anomalous coefficient R sub S equals 5 times 10 to the minus 8 cubic meters per ampere, magnetization M equals 8 times 10 to the 5 amperes per meter. Total Hall voltage. V sub H equals I divided by T times the quantity R sub OB plus R sub SM equals 0.01 divided by 1 times 10 to the minus 7 times, negative 2 times 10 to the minus 10 times 0.05 plus 5 times 10 to the minus 8 times 10 to the 5 equals 1 times 10 to the 5 times, -1 times 10 to the minus 11 plus 0.04, approximately equals 4 times 10 to the 3 volts. The enormous voltage shows the anomalous Hall effect term dominates. In real devices, the geometry limits the voltage, but the calculation illustrates why ferromagnets are used as magnetic sensors. These examples reinforce the formulas derived earlier and show how to move from measured voltages to material parameters and vice versa. A Hall probe is basically a tiny calibrated Hall sensor, packaged together with the necessary electronics to turn the tiny Hall voltage into a usable signal. Key design elements. Sensing element, usually a thin rectangular piece of doped semiconductor silicon, gallium arsenide, or a metal film. Thickness is kept small, a few micrometers, to maximize V sub h. V sub h equals IB over NQT. Current source, a stable constant current driver, often 1 to 10 milliamps, is integrated to ensure I does not drift with temperature. Differential amplifier, because V sub h is tiny, a low-noise instrumentation amplifier with high common mode rejection is used. Chopper stabilized amps keep 1 over F noise low. Temperature compensation, Hall coefficient varies with temperature approximately % per degree Celsius. Many probes include a thermistor near the sensor and apply a software correction. Packaging, the sensor face is exposed through a non-magnetic window, such as quartz or ceramic, so the magnetic field reaches the active region without distortion. Calibration steps. 0 field offset, place the probe in a magnetically shielded environment mu metal box. Record the output, this offset is subtracted from all later measurements. Sensitivity scale factor, expose the probe to a series of known uniform magnetic fields, such as using a calibrated Helmholtz coil. Plot output voltage versus B. The slope gives S equals V sub h over B. The linearity should be greater than 99% over the intended range. S equals V sub h over B. Temperature map, repeat the sensitivity test at several temperatures: 0 degrees Celsius, 25 degrees Celsius, 50 degrees Celsius. Fit a polynomial S of t and store it in the probe's firmware or calibration file. Directionality check, rotate the probe 180 degrees, the output should change sign, confirming correct wiring and that the probe is not picking up stray components. Practical tip, use a short twisted pair cable from the probe to the measurement unit to minimize induced voltages from external magnetic fields. By following these design and calibration practices, the Hall probe can reliably measure fields from a few microtesla up to several Tesla, with an accuracy of 0.1% or better. Hall-based sensors are versatile because they turn a magnetic field into an electrical voltage, which is easy to read with electronics. 1. Magnetic field sensing. Gauss meters, handheld instruments that contain a calibrated Hall probe. The user points the sensor at a magnet, and the device displays the field strength in Gauss or Tesla. Useful in research labs, automotive assembly, checking motor magnets, and medical imaging MRI field verification. Position sensors. A small permanent magnet attached to a moving shaft passes close to a Hall element. The Hall voltage varies with distance, giving a precise linear or angular position readout. Common in electric vehicle throttle bodies and robotics. 2. Current measurement, Hall effect current sensors. Principle: when a conductor carries current I, it creates a magnetic field B equals mu naught I divided by 2 pi r around it. A Hall element placed near the conductor senses this field, so the output voltage is proportional to I. Since the Hall element is electrically isolated, the sensor can measure high currents kilo amperes safely. Typical architecture. First, a ferromagnetic core directs the magnetic field into a narrow air gap where the Hall chip sits. Second, the chip is supplied with a constant current generating V sub h equals R sub h I Hall B divided by T. Third, an internal amplifier scales the voltage to a convenient range 0 to 5 volts for a 0 to 100 amp input. Advantages: no direct electrical connection to the high current line leads to galvanic isolation. Wide bandwidth direct current to greater than 100 kHz, useful for power electronics switching. Linear response if the core and sensor are designed correctly. Applications: battery management systems, motor drive current feedback, protective relays, and smart grid monitoring. 3. Speed rotation measurement. Hall effect wheel sensors. A tooth wheel or magnet array rotates past a fixed Hall sensor. Each tooth or pole produces a pulse of Hall voltage, which a microcontroller converts to revolutions per minute. This is the basis of anti-lock braking systems, ABS, and engine crankshaft position sensors. 4. Contactless switches. Proximity switches. A small magnet on a moving part approaches a Hall switch. When the field exceeds a threshold, the Hall element turns on a transistor signaling that the part has reached a specific position. Used in door open detectors, conveyor belt indexing, and consumer device lids. Overall, the Hall effect bridges magnetism and electronics, enabling robust non-contact measurement solutions across many engineering fields. The Hall effect is a standard lab tool for characterizing semiconductors because it simultaneously gives two key parameters: 1. Carrier type, N-type versus P-type. The sign of the Hall voltage tells you whether the majority carriers are negative electrons or positive holes, by simply reversing the magnetic field direction. And noting the sign change, you can confirm the doping type without any destructive test. 2. Carrier concentration N or P-, using the measured Hall coefficient R sub H equals V sub H times T divided by I times B, and the relation N equals 1 divided by absolute R sub H times Q, or P equals 1 divided by absolute R sub H times Q for holes. You obtain the density of carriers per cubic meter. This number is crucial for device design, for example setting the junction depth in diodes. 3. Mobility mu dash mobility links how quickly carriers move under an electric field: mu equals sigma divided by absolute Q times N, where sigma is the electrical conductivity measured separately using a 4-point probe. High mobility means faster transistors and lower power loss. Practical procedure: Step 1. Prepare the sample, a thin rectangular slab with known thickness T and width W. Step 2. Contact placement: 4 contacts. 2 for supplying current along X, 2 for measuring Hall voltage across Y. This geometry Van der Pol reduces size constraints. Step 3. Measurement. Apply a constant current I, for example 1 mA, turn on a calibrated magnetic field B, for example 0.2 Tesla, and record V sub H. Step 4. Compute - First calculate R sub H equals V sub H times T divided by I times B dash. Then calculate N equals 1 divided by absolute R sub H times Q, or P dash. Measure resistivity, ρ equals R times A over L with the same contacts. Then sigma equals 1 over ρ dash. Finally mu equals sigma divided by Q times N. Example: a silicon wafer, thickness 300 micrometers, measured Hall voltage 2.4 millivolts for current 5 milliampere and magnetic field 0.1 Tesla. R sub H equals 2.4 times 10 to the minus 3 multiplied by 3 times 10 to the minus 4 divided by 5 times 10 to the minus 3 times 0.1 equals 1.44 times 10 to the minus 3 cubic meters per coulomb. Assuming P-type, P equals 1 divided by 1.44 times 10 to the minus 3 times 1.6 times 10 to the minus 19, approximately 4.3 times 10 to the 21 per cubic meter. Measured resistivity ρ equals 10 ohms centimeter, gives sigma equals 100 Siemens per meter. Mu equals 100 divided by 1.6 times 10 to the minus 19 times 4.3 times 10 to the 21, approximately 0.145 square meters per volt second, equals 1,450 square centimeters per volt second. These values are typical for moderately doped P-type silicon and directly feed into device simulations for MOSFETs, solar cells, and sensors. Why it matters: mobility and carrier concentration govern switching speed, leakage current, and optical absorption. Hall measurements give a quick, contact-free snapshot of these properties, helping engineers optimize doping profiles and material quality. Advanced characterization: temperature-dependent Hall. By measuring R sub H and mu from 77 Kelvin to 300 Kelvin, you can extract scattering mechanisms, phonon versus impurity. Plots of mu proportional to T to the minus M reveal the dominant process. 2. Carrier analysis. In compensated semiconductors where both N and P are present, the full expression R sub H equals parentheses P mu sub P squared minus N mu sub N squared divided by Q times parentheses P mu sub P plus N mu sub N squared close parentheses squared is fitted to data taken at multiple magnetic fields, yielding separate n, p mu sub n, and mu sub p. Explanation below is a set of typical exam-style questions together with step-by-step solutions. They cover theory, derivation, and practical calculations that students often encounter in engineering physics courses. Question 1. Derive the expression for Hall voltage for a rectangular slab carrying current I in a magnetic field B. Step 1. Write Lorentz force on a carrier, F equals QV sub D cross B. Step 2. In steady state electric field EY balances magnetic force. QEY equals QV sub dB, therefore EY equals V sub dB. Step 3. Current density J equals NQV sub D, so V sub D equals J over NQ, which equals I over NQ TW, since J equals I over WT. Step 4. Hall voltage is the integral of EY across width W, giving V sub H equals EYW equals IB over NQT. Step 5. The Hall coefficient R sub H equals V sub HT over IB, which equals 1 over NQ. Question 2. A copper strip of thickness 0.1 mm carries 3 amperes and is placed in a uniform 0.4 Tesla magnetic field perpendicular to the current. Compute the Hall voltage. For copper, carrier density and approximately 8.5 times 10 to the 28 per cubic meter. Charge Q equals minus 1.6 times 10 to the minus 19 coulombs. V sub H equals IB divided by N absolute QT equals 3 times 0.4 divided by 8.5 times 10 to the 28 times 1.6 times 10 to the minus 19 times 1 times 10 to the minus 4. Numerator equals 1.2, denominator approximately 1.36 times 10 to the 6. V sub H approximately 8.8 times 10 to the minus 7 volts, which is 0.88 microvolts. The tiny voltage explains why Hall sensors for metal field measurement usually employ very sensitive amplifiers. Question 3. A Hall sensor made of N-type silicon with carrier density 2 times 10 to the 22 per cubic meter has thickness 200 micrometers. If a current of 2 milliamps flows and the magnetic field is 0.1 Tesla, what Hall voltage is produced? V sub H equals IB divided by NQT equals 2 times 10 to the minus 3 times 0.1 divided by 2 times 10 to the 22 times 1.6 times 10 to the minus 19 times 2 times 10 to the minus 4. Denominator equals 2 times 10 to the 22 times 1.6 times 10 to the minus 19 times 2 times 10 to the minus 4, which equals 1.024 times 10 to the 0, i.e. 1.024. Thus V sub H equals 2 times 10 to the minus 4 divided by 1.024, approximately 1.95 times 10 to the minus 4 volts, which is 195 microvolts. Question 4. A Hall effect current sensor uses a ferromagnetic core with an air gap of 0.5 millimeters. The Hall chip in the gap has Hall coefficient negative 5 times 10 to the minus 9 cubic meters per coulomb and is biased with a 5 milliampere current. If the measured Hall voltage is 25 millivolts, what is the primary conductor current? The magnetic field in the gap due to the primary current is B equals mu naught I over 2 pi r. But for a core, we treat B equals mu core I primary over gap. Assuming the core drives the flux so that B equals K I primary with K equals 0.1 Tesla per ampere, typical for a small sensor, we use the Hall voltage formula. V sub H equals R sub H I Hall B divided by T. Here I Hall equals 5 milliamps. T equals 0.5 millimeters, which is 5 times 10 to the minus 4 meters. B equals V sub H times T divided by R sub H I Hall equals 0.025 times 5 times 10 to the minus 4 divided by negative 5 times 10 to the minus 9 times 5 times 10 to the minus 3. Numerator equals 1.25 times 10 to the minus 5. Denominator equals minus 1.25 times 10 to the minus 10. Therefore B equals minus 100 Tesla, the negative sign indicating electron carriers. The magnitude 100 Tesla is unrealistic. This indicates the assumed K is too small. Lesson: in exam problems, the core flux relation is usually given. Using the correct factor yields a primary current of a few amperes. Question 5. Explain how Hall measurements can be used to separate electron and hole contributions in a compensated semiconductor. Step 1. Measure Hall voltage at several magnetic field strengths. The Hall coefficient R sub H will vary non-linearly if both carriers are present. Step 2. Measure the conductivity sigma independently. R sub H equals P mu sub P squared minus N mu sub N squared divided by Q times P mu sub P plus N mu sub N all squared. Sigma equals Q times N mu sub N plus P mu sub P. Step 4. Solve the two equations for the four unknowns. With additional data, for example temperature dependence, you can uniquely determine N, P mu sub N and mu sub P. Step 5. Plotting R sub H versus B often reveals a sign change, confirming the presence of both carrier types. Question 6. A Hall probe is calibrated using a Helmholtz coil that produces 0.01 Tesla, 0.02 Tesla, and 0.03 Tesla. The corresponding output voltages are 0.5 microvolts, 1.0 microvolts, and 1.5 microvolts. Determine the probe sensitivity and zero offset. Fit a straight line V equals SB plus V sub 0. Differences: delta V equals 0.5 microvolts per delta B equals 0.01 Tesla. Therefore, sensitivity S equals 0.5 millivolts divided by 0.01 Tesla, which is 50 millivolts per Tesla. Using the first point, 0.5 millivolts equals 50 millivolts per Tesla times 0.01 Tesla plus V sub 0, giving V sub 0 equals 0. Hence, the probe has a linear response with zero offset, approximately 0 microvolts, and sensitivity 50 millivolts per Tesla. Tip for students: always write down the geometry, thickness, width, current direction, and sign conventions before plugging numbers. A small sign mistake can flip the interpreted carrier type, which is the most common error in Hall effect exams.